Okay. Is this working? Is the sound okay? Okay. I don't think you guys are hearing me. No, you don't? Okay. Take your time. You're paying for the lecture. So if you don't want it, that's also great for me. Okay. Welcome to your Friday entertainment / lecture. So yesterday, we started talking about combinational circuits. We said that combinational circuits is one of the two types of circuits we'll be dealing with. And we said that they are great because they don't have any memory. And what we started discussing, was that, we would want to have a functionality. You guys are okay? Everything okay? Okay. I'm, slightly threatening. Okay. So we wanted to talk about the functionality, and we saw that given any functionality that we want, we can convert them into Boolean equations. And once we have the Boolean equations, we can maybe modify them and get a optimized version of those equations. Anybody remember why we cared about, we have an equation, it works. Why do I even care? Anybody? Oh, many people. Okay. Let's say from the back, yeah. Because of money, yes. And why is money involved in this? Anyone else? Yeah? Okay, so the money equals area, meaning that the more circuits I have, the more circuits I'm putting together, the more I have to pay. It could also have implications on speed. It could also have implications on power. So we have an interest in not only having any logic equation, but once I have a logic equation, it might actually pay off to look at it and see, are there any smart ways that I could minimize this equation, which does exactly the same thing, but, cost less, which is something good. So what we then started looking at was something funny that we call Karnaugh maps. And I'm just going to quickly jump through to give you the idea. We had a problem, the problem was this giant scientific problem about lunch, cabbage, open cafeterias, and things like that. It's a funny example. It's maybe not very exciting, but it shows you that from a problem that you describe as a human person, one person to another, where you're making a decision based on a certain factors, you can actually formulate it in a truth table. And once you have it in a truth table, we saw some definitions and descriptions that we saw that anything in a truth table can be written as a function of its input. So you know what the output is going to be. And we learned that there is a sum of products form that allows you to express it. And we went on a little bit more. We had a couple of discussions. We said mean terms, max terms. But just looking at the table, we can just go down and write an equation, which is great. And then we were talking about it, and we said, hey, there are a couple of ways that if you look at this equation, and somebody pointed out and says, like, look, Frank, I mean, why are you needed? Why do you write an equation? Look, B is exactly equal as Y. Well, that requires you mentally to put an effort into it and requires you to take advantage of, let's say, your human cognitive capabilities. If this was a bit more complicated, maybe, I mean, it wasn't that blaringly obvious to some of you, still you might have out of this truth table written a larger equation, and then you might have realized, hey, there's a way to simplify it, and the simplification makes life a little bit easier. So then we came to this Karnaugh maps, and this is where we left, and we will continue after that. But we had a truth table, and then we realized that, hey, these variables, we can write them here. So if there are 8 outputs, I can make a box with 8 outputs. On the top, I have A, B. So A, B can be 0, 0, 0, 1, 1, 0, 1, 1. I'll write all of them. The only trick we are doing here is, when we are writing these columns, we don't go 0, 0, 0, 1, 1, 0, but we make sure that we only change one of these bits. So we go from 0, 1 to 1, 1, then 1, 0. Now we write in our numbers, and what we try to do is circling these guys in as much as we can, like whoop. And we realize that this circling of powers of 2, so making a circle of 1, 2, 4, 8, 16, whatever, is helping us identify actually which one of these implicants are part of the formula. And it's a sum of products, right? So we realize, for example, instead of having this guy being expressed at not A and not B and not C, or not A, not B, C, we realize that the C doesn't really play a role, and Y will be equal to not A, not B. I saved a little bit. Yeah, I'm happy. So then we had a larger example. Just to refresh it, I sort of randomly created a truth table. I have to press this, I guess. Yeah, sorry. Too many instructions here. Okay, but now I move this way. Ah, great. And now? No? Okay. I don't know if it's visible, but I have a truth table here, A, B, C, D. I have Z, and now I have made my Karnaugh map according to that. And don't worry, I'll also draw something that side. So it goes 0, 0, 0, 1, 1, 1, 1, 0, and I copy these in hopefully correctly, okay? I don't want to have my miss already. So how can we find if I have what formula we can have? So help me out here. Anybody who sees a nice large, yeah?
First 2 boxes.
Like these 2. Okay, you sure you want to take that first? Yeah. Go for the big ones. Yeah, and the you want to take them like this? Yeah. Okay. Why not? Okay. Like this. Okay. Yeah, more people, yeah.
I would again take all corners in the second column.
All corners. Well, okay, the second column. Let's take the second column first, because that is looking in our faces and saying, please take me. Right? Please take me. And now, actually, I don't have so much against this thing, but somehow, you know, your corners, you know, so there's no disrespect. But if you're looking at it, we can cover it a lot of times, but maybe it would have been smarter to take the corners, because I would have this guy, this guy. These were already covered because that's a nice column. And then I could have taken this guy away. As you see, there are many different alternatives. Somebody was asking, how do you know this is the best one? Well, we don't usually. And it's a little bit of guesswork involved. I'm very sorry to say. I'll go with the corner guy. Okay. Well, I mean, the other one would have also worked. You know, there's nothing wrong with it. It's just that this solves me a further problem. This guy is remaining. Someone? Yeah? No, please, you. No, oh my God. I'll just draw it, okay? I mean, before you can answer it. Okay. So, what is our function now? Let's start with the corner. Yeah? No? Anyone? Well, you know, sorry. You already set the corners. Someone else. Yes? Not B and not D. Are not D, yeah, and not B. Yeah, that looks correct. Plus, there's an easy one. Always pick the easy ones first. This guy? Yeah? Not A and B. There's one more remaining. Yes?
A and not B and not C.
A and not B, that's this part, and then not C. Bless you, that's it. We've managed it. We've done the entire, I mean, it was a, let's say, randomly defined function. It was also not the smallest function, but we ended up, first of all, finding what it is. If you were to write down the products of sums, we realize that these are the min terms, right? So I have to have this one, I have to have this one, then, my God, all these four, then this one, then this one, then this one. I'm getting tired drawing it. So if you were not minimizing it, I would write, if you were not minimizing it, I would have written not A, not B, not C, not D, or the next one, not A, not B, C, not D. The next one, this guy, not A, B, where are we? Not C, not D. Plus, you know, and I would go on and on and on and on and on. So if you're thinking that this was a lot of work, just think about it. If you're writing this in your exam, there were 9 min terms here that I had to add. So this thing would have gone on. So compared to this one, which is short, I have much less chance of making a mistake that also makes our life easier to minimize it. Not only the speed and the area, being able to put this smaller has some effects. Okay. Questions so far on these before I go on, continue with today's lecture? Yes. Yes. Fortunately. Otherwise, you know, making those bigger things would take a lot of time. Oh, sorry, there's a question on the chat. The corners. Yes. Let me put the chat here. Sorry. Okay, I'll manage this. Okay. And so this was the example that we drew the last time. People were leaving, so you realize here was an X, and the temptation is also take the X, right? You don't have to. You realize that, hey, just because this guy, I'll just assume it's 0, and so I won't take it. Because it's an X, every X can be treated differently. So these guys was beneficial for me to take them as a 1, and this guy was beneficial for me to take 0. So this is what I did. Okay. So this comes directly to the question, is this any useful? So people who are doing the latest NVIDIA Grace Hopper, whatever, are they using this to design their circuits? The answer is no. Okay, they are not. So in modern engineering practice, computer programs called logic synthesis actually take your description and are able to make all these moves and optimizations and come up with a set of gates, interconnected gates that we will call netlist, and tell us and give us a result. However, it is still good practice for us to learn what goes into this, what is needed, what do we need to do, so that you know, we can put these things together. So for the Karnaugh maps, you can do 2, 3, 4, that's not a problem, and we will ask in exams. But 5, 6, hardly doable. Anything larger, not possible. And it's useful. It allows you also to understand the logic functionality. Now, I have, after some description, a logic formula. The logic formula is nice, right? So there is some inversion, some things. How do I convert this to a circuit? And we realized that we had a set of circuits, AND gates, OR gates, that magically came out of the transistors. We were not going into how they are designed. We just know by combining PMOS and NMOS transistors together, we are able to make efficient implementations of basic AND and OR functions, inverters, XORs, etc. So if I have some function like this, how do I come to a circuit? And we realize the following, that if we use sum of products, the inner part of the parenthesis is always an AND function. I take the inputs, I take their complements, and I just AND them in groups of 2, 3, whatever. And then that's the first level. And in the second level, I'm going to OR them. So by drawing, we can make something like this. So here you see your input. Here you see its complement. So these are our literals. We have A, not A, B, not B, C, not C. And now, actually, all my min terms are here. I have not A, not B, not C. I have A, not B, not C. I have A, not B, C. So these are those three guys. 1, 2, 3. That goes here. The middle one goes here. That one goes here. So I have three outputs, and I OR them together. Now, technically speaking, this is it. Any combinational circuit in this world can be mapped to the Boolean logic functions in sum of products or product of sums. We would be changing ANDs and ORs. And we can just sum them up, and that's it. Okay? Lecture over, let's go home. Okay. So all of a sudden, we had something that looked like a mathematical formula to something that looks like electrical engineers are doing. So there is a circuit schematic that describes what type of things we are doing, what signals are coming, how they are connected. So once again, we are doing this also for you to be able to follow when you are confronted with these schematics, to understand what's being said, what's being explained. So for the circuit schematics, there are a couple of simple ideas. So they say, let's keep things simple. We can obviously make it more complicated, but you say, the inputs should come either from the left side or from the top, and the output should go out on the right side or the bottom. As a convention. Of course, you can do all kinds of funny things. My inputs are in the middle and the outputs are shining up. Yeah, exactly, right? Why would you even do that? And so the circuits, usually you see it like a water flowing. They get processed from the inputs and they appear at the outputs, or they are flowing here from the top to this side. That's a more natural way of thinking for, let's say, people who are trained in these things. So we would advise you also to follow it. It will also help you identify things when you're looking at circuit diagrams. Now, the other one is straight wires are usually much, much easier on the eyes. So one question that a lot of people do is, how do wires connect? So if you are, like you have one wire that goes this way, and another wire comes here, there is like this tendency to say, I'll jump over this and make a drawing like this. Now, this is fine if you're making one of them, but if you have like 7 wires coming and you are like jumping up and down, it sort of kind of gets annoying. So one of the things that we say, if there is a wire and you make a T connection, these guys are connected. So it's assumed that this one and this one is connected. When they are crossing over like this, if you want them to connect, we will put a crossover dot to make sure that they are connected. Otherwise, if they are just crossing without anything, we will assume that these 2 wires are at different levels, they don't connect. It's a drawing convention, okay? This is not physics, it has nothing to do with it. So if you follow this convention, and I can go back to the drawing that we had in a second, disappear. Let's go back to the drawing that we had. You see these things happening here, right? So here, A is connected and is going this way, but this A is now jumping over. They are not being shorted. So A is not shorted to not A, it's not shorted to B. It just goes and connects here. The same way, the min term goes this way and is connected here, but it jumps over this min term, A not B not C. This avoids all these funny squiggly things jumping over. Good. I like that. There's a very positive person there. Helps me straighten it up. Okay. This is about drawing circuit diagrams. You might be asked to, interpret a circuit diagram. You might be asked to take a look at it, but they will not be ridiculously complex. However, given a circuit diagram that consists of AND or XOR inverter gates connected, you are expected to follow what's going on there, talk about it, reason about it, and solve a problem or two. Now, what we talked about is that we have something that has one output. So this is what we described. What happens when we have multiple outputs, like this circuit? There is like 4 inputs and 4 outputs. And the output is also kind of described funnily. Output is the most significant true input. So if I have a pattern that says 0, 1, 1, 0, the most significant bit would be A2. So the output should be Y2 is 1, and all the others are 0. I just fill the truth table. And I have actually here 4 separate circuits. This one is the output Y3, for which I can draw a Karnaugh map, optimize it, minimize it, or just realize that this thing is exactly this. I can have another one, I can have another one, I can have another one. They are actually independent. And then when I'm drawing it, I can, so we can write the sum of products, reduce the equations from the functional description. And sometimes we can just, look at it, like without drawing the Karnaugh diagram. This is the same thing I was explaining, saying, Y3 is true whenever A3 is asserted, so Y3 is A3. So, this is us, again, spending time in it. And once we have the equations, we can just write down what they are. And we realize it's a relatively simple circuit. A3 goes directed to Y3, A2 goes to, it is not A3 and A2, and then the next one is not A3, not A2 and A1. The other one is not A3, not A2, not A1, and A0. Yeah, we made a circuit. Now, sometimes writing such a long truth table is annoying. It took me like 2 minutes to write it. And then when you realize you can sometimes compress the tables by putting don't cares. Like in this case, you realize that the moment A3 is 1, you don't really care what A2, A1, and A0 is. They can be 0, 0, 1, 0, 1, 1, whatever. So you can actually capture this a little bit quickly and say, A3 is 1, the rest can be zeros or 1, the output will be this. Notice that it carries exactly the same information. It just lets you type less. And the less you type, the less you make mistakes, actually. The less when you communicate, you make a mistake. So there is also an advantage to be gained there. It's a very quiet class. No. Question? Yes?
What if we have one output, then we have it?
Yeah, I mean, because this doesn't depend on it, right? You could have, theoretically, you have 16 different numbers. How many different 4 input functions can we have? Direct exam question, by the way. What do you say? How many different 4 input logic functions can we have? There's already a hand rising, yes? 2 to the power of 4. Okay. Anyone says that's more? What's 2 to the power of 4? 16. So you think, there's 4 of them here. You think there are only 12 additional ones? Not likely, right? There seems to be more. Who says there's more? I say there's more. Yeah, okay. How many? How many different bits do you have here? How many different rows do you have? Yes? So how many combinations are there? 2 to the power of 16. That's a bit more than this, right? How much does it make? Anybody remember it by heart? Approximately? About 64,000, yeah. How do you say it? Because it's 2 to the 6 times 2 to the 10. Right? So 2 to the 6 is 64 times 2 to the 10 is 1,000. So about 64,000. If you're a real geek, real geeks, oh, come on, there are geeks among you. No? 65,536. That is 20-something years or 30 years of electrical engineering for you. Don't be like me. But very good question. So you can have as many as you want, you know, I mean, the same inputs, there is not yet 100,000, but more than 50,000 different functions that can be defined. You can just go. There are blackboards all over the place. You can make Karnaugh maps until you drop. Now, we've been using these things for quite a while. We use ones and zeros in our circuits, and sometimes we were talking about these X's. I just did. So it's clear that these ones and zeros are not the only things we should be caring about. There are also some other characters involved, and this is where things get a little bit messy. We need these slightly strange signals, and notice that these signals will not encode information. It's not like there is an additional value. It's not I have 0, 1, X, and Z. Those things are strange things that I need to cover. They are exceptions. They are problems. They are bad memories, if you want. And so these are cases where the output is neither 1 or a 0. Or maybe it is one or the other, but we just don't know which one is. Now, there are two cases. And remember, if you have a circuit whose two outputs connect to each other, we said that's not a combinational circuit, right? Yeah? Nothing? Right? Oh, yeah, okay, there's a little thumbs up. Sometimes there's a 2 thumbs up, and then there's a little thumbs up. Okay, so, but, you know, okay, I agree, these are combinational circuit rules, but, you know, how do we know if someone is breaking them? If someone is breaking them, we should also be allowed to, or if we are a simulator, if we are any computer program, we should be able to say, excuse me, sir, those two things, I mean, there's a problem. And if I have only a 0 and 1, I won't be able to express this problem. I need a separate signal, separate value, separate kind of thing to say, dude, here's a problem. These two things connect. And you know, when these two things connect, there's a chance that they are both agreeing, right? I mean, this is one person that says, yeah, it's 0. And this person says it's 0. But what happens if this guy says it's 1 and this guy says it's 0? What will happen? Anybody? Anybody apart from here? Oh, yeah, there. Sorry? This guy says it's 1, this guy says it's 0, and you think it's going to be 1. Why? Well, I don't know. You might be, how shall I say, 1 biased, you know, thinking that the opinion of 1 is better than the opinion of 0. You know, a 0-2 movement would be against this. Yeah?
Maybe the one which is quicker.
Yeah, but from its structure, we cannot really tell. Maybe one of those guys is stronger than the other. Like there is this tiny guy saying, it's 1. And then there is this big burly guy saying, it's 0, okay? And then it will be 0. Maybe they are both the same. I don't know. The problem is, our discipline doesn't capture these things. We want to know when it is definitely a 1 and definitely a 0. We don't want to have any contention. So if there is any time such a contention, we are going to use X. That's the thing. I don't want to be having this discussion like, yeah, you know, in these cases in Northern Hemisphere, 1 is all. We don't do that, okay? Then we have another problem. And there will be cases when we want to do this. There will be cases when we want to do this. I'm sorry, I know I'm confusing. But we know that the problem is that they both cannot drive at the same time. There will be cases because the resources for interconnection can be precious. If you think about the computer, there's memory, there's many memory banks, and we don't want to connect them to separate wires. We connect them next to each other and say, okay, at any given time, one of you will talk. Then we don't have a problem. If both of you talk, I have this problem. But at any given time, if I can ensure that only one person is talking, we are fine, which is good. But I need a case where I can tell that this circuit is not talking. He doesn't count. And we will call this the high impedance state, meaning that the guy is there, but he's not really part of the discussion. He's not driving its outputs. He lets his output go any way you want. He's not arguing against you. So this thing would be an issue. However, if this guy, while this guy is driving, when this guy is saying, hey, the output is 1, if this guy is in high impedance state, this state, then the output is whatever this guy says it is. And then at some point, we can reverse roles and say that, okay, now it's your turn to speak. He can drive whatever he wants. And this guy has to disconnect itself and say, I'm in high impedance state. I don't care what you are doing there. Now, yeah. Now there are some issues. I'll go into both of them. So now the contention, let's go back to the contention, 2 outputs, this is a problem. But remember, I also used X as a, I'll come back. I also use X as a don't care. And they're not the same, because contention is at the output, the don't care is at the input. This is a slight problem, which I will address beginning of next week. When we describe circuits in a way that allows us to write it like a program, we call it hardware description languages. Back in the 80s, people developed 2 different languages. One of them was called Verilog, and in our lecture, we will cover Verilog. And in Verilog, these are, well, they are fairly relaxed about rules. They don't want to cover too many things. And that's like the lazy person's, yeah, let's just both call them X. So in Verilog, uses X for both of them. VHDL, on the other hand, very similar language, does exactly the same thing. Hard to say which one is better. Both are used, although these days, Verilog is used slightly more. 10 years ago, they were more or less the same. VHDL is very, very specific. It has tons of extra characters. It says, don't care is not the same as contention, is not the same as I don't know its initial value, is not the same as, and you know, he has different characters for all of them. Verilog puts everything together. It's a bit confusing when you see it in textbooks that might be more geared towards VHDL. You will see different characters. In textbooks like ours, which is on Verilog, you will see them both mentioned at the same time. Okay, now the floating, the high impedance, the Tristate Z, whatever, high Z kind of thing, has 3 different outputs. It can be 0, 1, that's defined, or somewhere in between. It's not really somewhere in between, but it's like that output is not driving. That output is not speaking. It's muted. I press the mute button. Sorry, I thought I'm in mute, right? That button, zoom kind, you know, it's also Z. Joke is not coming, okay, good. So it works normally, except that when it's not enabled, you have this thing. So why is this useful? Once again, this is more like a shared connection between many things. You might have a processor at the top, a video interface, an Ethernet interface, a memory interface, and they all want to communicate over a shared resource. Why? Because those shared resources might be big, there might be a lot of wires, and I don't want to have separate wires going from processor to video, separate wires from video to Ethernet, separate wires from this to that, because it will create a lot of wires. And at some point, we might have said, let's use a shared system. If you have a shared system, we run into the problem that we may not have a combinational circuit if two of them, if both Ethernet and memory try to write something to the shared bus, we will have a bunch of X's. Not good. So we have these tri-state buffers which help us isolate, and at any given time, only one of these people are driving the output. So something that we don't see here has to do this control, has to do this regulation. So it's either the video driver, then EN2 is enabled, all the rest, EN1, EN3, EN4 are disabled, making this person the only one that is writing to the, or outputting to the shared bus. And then there's an agreement, maybe they say, okay, talk for a minute, and then it is this guy's turn, or maybe there is some sort of other control that regulates who can speak when, but all of these parts know that, or the system is made in a way that we respect the combinational circuit discipline by making sure only one person is driving. This usually has a lot of questions, so how does it look? Wow. Frank, what an explanation. Everybody got it. Okay. Ask the questions also later, don't worry. Now, we are trying to round up this thing. There are a couple of building blocks that are very commonly used. They are so commonly used that we will refer them with their names, although you can still write a truth table and write the min terms, max terms, and pause, SOP, minimize it, and come up with the descriptions. It's just that they are super, super useful and are used a lot. So I want to just mention a couple of them. This is my favorite, the multiplexer. I mean, it's like the cutest circuit in the world. What it does, so it's drawn like this. There is a signal that we call select, usually. That's why the name S. And it selects between two inputs, either D0 or D1. And it's very simple in its mind. You say, if select is 0, the output D0 should be, the input D0 should be copied. If select is 1, I take D1. More or less, this is an if then else in hardware. Right? Isn't it great? I love this thing. No? Is this okay? Yeesh. That part also? Next to you? The reaction is like completely frozen. Don't talk to me. Okay. So you can, 2 to 1 is, we call this a 2 to 1 multiplexer. Why? Because we have 2 inputs, 1 outputs. You can then combine this into larger systems. You can have a 4 to 1 multiplexer, which is even more awesome, you know. And you can express this in different ways. You can write the sum of products form if you really want. You can even have like this funny tri-state kind of thing where you realize I have 4 inputs, and at any given time, the select signals only enable one of them, and the rest are high Z. Or the real way, what a lot of people would do is use 2 levels of 2-1 multiplexers. So this guy selects between D0 and D1. This guy selects between D2 and D3. And then we go to a playoff, and the final is between the winner of these 2 and the winner of these 2. I love this circuit. I cannot tell you how much I love this circuit. Okay. Question.
Does S0 control photo?
Yes. So if S0 is 0, this guy will select D0, and this guy will select D2. And then S1 will select between D0 and D2. Yeah, question.
Are multiplexers with multiple outputs, or are they, do they exist? So not 4 to 1, but 4 to 2.
Well, that would be actually 2 multiplexers side by side that have the same input. There will be like, you know, this is one. There will be another one that has something. So yes and no. You know, you could build structures with things. But what you use it, of course, is Now we are just looking at one bit, which is kind of annoying. You could imagine that this is a big bus of 64 bits, and you're going to have a 64-bit 2-to-1 multiplexer, and you either choose like this big 64-bit value or that 64-bit value. In terms of transistors, actual gates, there will be 64 of these people parallel, and they will be steered by the same control signal. And in a lot of digital circuits, it's a very common building block, especially in computer science, people, or in computer architectures, multiplexers are used more than they should, let's put it that way. Anytime you have an exception, say, let's have another one, let's have another one. Because it's such cuddly and cute building block, we tend to overuse them. Now, multiplexers also have very cool properties. There's a reason I love them, right? So technically, you can implement any logic function with a multiplexer. Here's an example. You say, I'll take this one, okay? You say you want y equals to a or b. Okay, how can I do it? And you can say, you know, if a is 0, the output will be this thing, which is exactly the same as b. And if a is 1, the output will be, well, this is 0, 1, and the output is 1, 0, which is just the inverse of this. So you say, if a is 0, the output is b. If a is 1, the output is not b. Once you write this, you can say, okay, depending on a, if a is 0, the output will be y. The output will be b. If a is 1, the output will be not b. Universal logic building element. How great is that? You could also have it more complex, right? In this case, like a and b, you look at it and say, hey, if a is 0, no matter what happens, y is going to be 0. And, you know, this thing doesn't always have to be a variable. It can also be a constant value, like a 0 or a 1. In this case, we tied it to ground. So this signal means ground, 0, low level. We could also tie them to high level. And for the high level, let's go to this thing. There is a big Karnaugh map. It has 3 inputs, and you know, I could write down these things, make my Karnaugh map magic, or I'm lazy. I take a multiplexer and I say, well, ABC, if it's 0, 0, it's 1, then it's 0, 0, then it's 1, 1, 1, then it's 0, 0. Hey, there you go. All this big deal of making a logic has disappeared. Honestly, though, this thing is not such a small circuit, so we are not looking at something small. You know, there is a very real place where this is used a lot. In FPGAs, field programmable gate arrays, that we use in our exercises, we are talking about that there are these universal building blocks, which have what we call a lookup table that can realize any logic function. Guess what is in there? This thing. Okay, larger ones, similar ones, but this is the logic behind it. So what you can do is, in an FPGA, you can reprogram the input of these things so they are not tied to 0 and 1. There is a configuration bit that allows them to be anything you want them to be. Okay. No, that wasn't a question. Okay. Let's take another circuit. This one is also very common. This is what we call a decoder. In our case, we have in this case, we have a 2-bit input, A0, A1, so there are 4 different things. And we want that only one output is active at any given time. This is a very useful circuit. This will be a building block in many of our things. So it's also nice to look at it. So how do we do this? Well, that was actually the question, right? I have 2 inputs and 4 outputs. So it's entirely possible. And Y3 is 1 only when A1 and A0 is 1. Y2 is 1 when only this mean term. And this one is only this mean term. And this one is only this mean term. Right? So if you look at it, you have A1, A0, And so Y0 is not A1 and not A0. Y1 is not A1, A0. Y2 is A1, not A0. Y3 is A1 and A0. So all 4 combinations come in here. And this will be very practical when we are building memory structures, where, long story, in 5 weeks, 6 weeks, we will be discussing these, where we apply an address, and only one of those outputs will activate. At any given time, you activate only one of them. Now, there's a side benefit of these guys, and that side benefit is, since these are the min terms, a decoder generates min terms, you already have the min terms, and you can OR them and get any logic function you want. So both multiplexers and decoders, if you have them available, if they are already in your pocket for some other reason, you could also cheat and use them to realize logic functions, just because they exactly represent part of the sum of products operation. And since you can map anything to sum of products, you will have this thing. So if you don't have any questions, now it's a great time for a break. And then we will continue with timing and maybe make an introduction to Verilog. Okay. Okay, weekend will start after this lecture. So let's get started so we can get home earlier. Is there anybody sitting in that other classroom? Anybody in F5? Are you seeing me? Okay, there's so much space here, so you can come, so we don't have to, you know, waste electrons going the other way. No? Okay, they don't want to come. They don't like me, okay? That's okay. Okay, so up to now, the only thing that bothered us was the functionality. But we know that there is more about functionality, and we also sometimes care about, well, we care about money. That was a speed thing. We care about when we go to MediaMarkt and buy stuff, that it should work fast. So timing is also one of the things we care about. And timing is going to be a fun topic. Now, we have many problems with electronic circuits. And one of the problems is speed of light. Do you know anything that's faster than speed of light? No? Okay. Who thinks speed of light is fast? You'll be very wrong. Speed of light is ridiculously slow. And that's one of our main problems. It is really slow. How fast is speed of light? What do you think? Yeah? 300,000 kilometers per second. Sounds a lot, right? So if we go down in time units, 1,000th of a second is what? 1,000th of a second? Millisecond. 1,000th of a millisecond is something in between? Microsecond. 1,000th of a microsecond is nanosecond. Nanoelectronics. Then the next one is picosecond. Okay, it goes up. So nanosecond is something that we care about a lot, you know, because something that happens in 1 nanosecond, that's 1 billionth of a second, happens 1 billion times per second. Does that make sense? Something that happens in 1 billionth of a second, that means that it also happens 1 billion times. And what is 1 billion times? Well, it's giga, right? So you're talking about, when you say gigahertz, you're saying that something changes 1 billion times a second, right? So if your computer runs at 1 gigahertz, you are saying that my computer does something 1 billion times a second. That's basically what you're saying. What it does, we will still discuss. But this nanosecond kind of thing is an entity, a value that is very close to us, because your computers are running at 2, 3, 4, 2.5, whatever gigahertz. So it is expressed in, let's say, nanosecond or fractions of a nanosecond. Now, big question. How much does light in vacuum cover in 1 nanosecond? Okay, that much, 30 centimeters. You can do the math. That's the size of your laptop. If it is 2 gigahertz, if your laptop runs at 2 gigahertz, light would travel 15 centimeters in vacuum, not on electronic printed circuits, because there the poor electron is also hitting all kinds of things back and forth. So it's traveling maybe at 60, 70% of the speed of light. So, only 10 centimeters. At 3 gigahertz, we are at, that's not much, okay? Look at your cell phone, look at your laptop, 10, 20, 30 centimeters is not much. And this is one of our issues, because we cannot move anything faster than speed of light. we will soon realize that making these circuits is going to be an issue, just by the nature of the one limit that we have in physics. Thanks, Einstein. If he just added a few zeros to that thing, life would be so much better. MediaMarkt would have great sales. We are stuck with gigahertz computers. Okay, so until now, when we looked at a logic circuit like a buffer, we saw the input and we said, hey, if the input is 0, the output is 0. If the input is 1, the output is 1. Oh, okay, great deal. We had the AND gate, OR gate, multiplexer, any one of them. We just say these are the inputs, these are the outputs. However, real life is slightly more complicated. I mean, even an electron doesn't travel within 0 time across 30 centimeters. So an electrical circuit which is driving the output also doesn't happen instantaneously. So you change the input, A is at 0, and A says, now it's time to go to 1. So A, first of all, doesn't spontaneously go to 1. Yeah, it's like a little bit of like, oh, okay, we're going to 1. And now it's at 1. And now the output will follow, because that's the definition of it. If the input is 1, the output has to be 1. However, there will be some delay. This delay comes because of the physical nature of these things. Remember the lecture that I said, hey, I'm not going to give? Circuits, currents, capacitors, takes time to fill, yada, yada, yada. This requires some time until this time is, the circuit has completed. Now, we differentiate two different timing. We have the first one, which we call TPD, propagation delay, is the maximum time that the circuit has where the inputs change to the maximum time where the outputs stabilize. Okay? It seems like a very reasonable explanation. No? I mean, come on, it's Friday afternoon. What else do you want? That's good. Propagation delay, don't forget it. This is like, hey, I'm going to have so much fun asking questions in the exam about it, and you're going to complain so much about it. Now, contamination delay. It's very similar, but there's one more difference. You apply the inputs, the outputs may take some while to settle. You may say, hey, here's the input, and then the output says, great, the output is 1. Oh, no, what was it? It's 0. No, I'm 1, I'm 0. And after a while, it says, yeah, you know what? I agree, I'm also 1. So, contamination delay is the first time that the output reacts, given to an input. It's not necessarily the same as propagation delay. Okay? Years ago, I had an example, and my wife liked the example so much, now I'm forced to tell this example. Okay? She's not watching, don't worry. So, imagine a bear. Okay, a big, cuddly bear, and the bear is slightly asleep. He's like, doze off, right? So you come, approach the bear, and you pat him on the back, and says, hello, bear, what's 2 plus 2? Bear is sleeping, right? And it's like, huh? Like, turns around, looks at you, shall I eat you or not? And says, and then says, 2 plus 2, yeah, it's 4. Now, contamination delay is his first reaction. Okay, I apply the input, I tap him on the shoulder, he turns around, he looks at me, that's the contamination delay, something has happened. In the end, he gives a correct answer, which is 4, hopefully, and that's the time, that's the propagation delay. Who likes this example? Okay, so I have to keep on telling it. I'll change it to a kangaroo, punches me in the face. Okay, now, why do we have these things? Delay is caused by capacitance and resistance in a circuit. We are not going into the details. I'll spare you all the things. Just know that those transistors need some current, some electrons to move from one side to another. They travel not faster than speed of light, so that causes some delays. And we say it's not as fast as you think. Now, Why is it propagation delay and contamination delay different of a circuit? Well, it's not the same operation when you are trying to go from 0 to 1 and then later discharge from 1 to 0. That should be obvious to you, that I can ask in an exam. Why? It's a good one. Yeah?
Because 0 is nothing, and going from nothing to something is 0.
Very philosophical, but no. I like it. It's a good approach. No. It goes back to how we were discussing about the circuits. We said there are PMOS transistors that pull things up, and there are NMOS transistors that pull things down, meaning that different parts of those gates are used for pulling things up and pulling things down. So it's a complementary circuit. Half of the circuitry is for making sure the outputs go up. Half of it is there to make sure the outputs go down. And out of technical reasons and a lot of variations and a number of reasons I will not want to go into, unless you want to stay here 2 more hours, these can be different. They not always have exactly matching speeds. That happens. We may have to our circuit, to our combinational circuit, we have a set of inputs. We have A, B, C, D, whatever. They may not come exactly at the same time. Some of them may arrive earlier than the others. That can cause changes to the functionalities. And then there's always these issues that, physical circuits also follow problems of the physical world. In colder temperatures, things run faster. In hotter temperatures, they run slower and other things. Here is one example. And this example should also explain you what is happening. So I have A and B, followed by OR C, followed by AND D. Okay? And this produces my output. Now, this is a very regular combinational circuit. There's nothing fancy about it. But assume that I apply all the inputs at the same time, an assumption that's not necessarily true. And then, you know, that N1 will take some time to materialize. And then once N1 is materialized, I already have C was waiting there. And now the other guy is going to come. So N1 comes, so N2 materializes. And notice that I said every gate is going to have a delay. So this is not going to happen in 0 time. This will take 2 hours. This will take 3 hours. And then 5 hours later, I have this output. And then this guy will happen in 2 nanoseconds. So there you go. Now, this is what we call the critical path of the circuit. This is the longest path that goes, and it is, if the output depends on A and B or C, this will take a longer time for the circuit to calculate. Okay? But there's also a short path. So the critical long path is the propagation delay is 2 times the propagation delay of the AND gate. We are assuming these AND gates are identical and can drive things at identical speed, plus the propagation delay of the OR gate, which is here. So if this is 1, this is 1, this is 1 nanosecond, microsecond, whatever, the critical long path, the propagation delay of this circuit is 3 units. Whereas there is this other path, and it's entirely possible that we have a set of inputs where it's this guy that determines the output. And if D changes, Y will also change. And this happens really fast because he only goes through 1 AND gate. So the contamination delay is the contamination delay of the AND gate, and the propagation delay is 2 times the propagation delay of the AND gate, plus 1 time the propagation delay of the OR gate. Yes?
When working with FPGAs, will these sort of things be issues, or is it more for really small, state-of-the-art Intel 4 nanometer?
Okay, so it's an issue for any kind of digital circuit from 1980s until 2024. I mean, it doesn't matter where you're looking at. FPGAs actually use quite modern technologies compared to, because the FPGAs are very good because you are selling a lot of them. So FPGA vendors, maybe they are not at the 1.5 nanometer node, but they are very close to, let's say, state of the art. They are not far behind. Even in FPGAs, the same thing will happen. They don't have distinct AND gates and OR gates, but there will be, if this is your circuit and it has been minimized to this thing, part of it will be realized in one block of the FPGA, which is a propagation and contamination delay. And maybe this entire functionality will not fit into one FPGA block, and you have a second part, and you will have exactly the same things. It may manifest itself slightly differently. The values might be different, but the principle is exactly the same. Doesn't matter if you're using a technology from, let's say, 1980s or 2020s, you will have these discussions pop up in a lot of times. And right now, they might seem slightly irrelevant, which is true, but we are building up together to something great. This calculation will tell us how fast our processor works. So the longer the propagation delay, the less the megahertz, gigahertz. Sorry, yes?
Could you, if you like, added an intentional delay so that you eliminate this phase where the output is not like clearly defined? Could you then, in theory, like execute the circuit like in waves, like
you could
wait for everything to finish, but already start with the next input, and then
that's exactly what people did, and it wasn't a great idea. I'll tell you why. I mean, it's a very noble idea. It has great potential, actually. There's nothing wrong with the idea, nothing to laugh about. It's just very hard because as much as we define these things, notice that they have temperature variations, they have transistors matching, not matching. Trying to fight against physics is an issue. It has to work the same speed at Kuala Lumpur and in Anchorage and things, temperatures, ambient, getting hot, slow. It's difficult. It is used. There is a, we call it wave pipelining, for example. I mean, asynchronous technologies, wave pipelining uses them. They are harder, much harder than dealing with this. When faced with problems, sometimes the best solution is either you try to eliminate the problem, like the differences in timing or the indecision that we have to wait. Either you say, I'll eliminate it, that was your thing, or you say, you know what, this is happening. Let me find a smart way to get around it. And this is what we will do. Makes life easier for the majority of cases. But what you describe is also used. It's a it's a solid approach, it's used. Just, we don't want to teach it. It's a secret, we keep it to ourselves. No, it's just very, very difficult. Yes?
Is the propagation delay always larger equal to the contamination delay?
The propagation delay, by definition, is always larger than the contamination delay. Yes, definitely. I mean, contamination delay says the shortest time that a circuit can react, the output will not change before contamination delay. And propagation delay says, hey, the worst case, whatever happens of all the, let's be real. There are 4 different inputs, right? 4 different inputs could have 16 different patterns. And those 16 different patterns can follow 16 different previous patterns. So there is 256 different things that can happen here. And not all of them take the same amount of time. The simple thing is, if A, B, C, D were all 0, and the next time they are still all 0, nothing will change. The circuit will look like it doesn't react. Doesn't mean that it doesn't have a contamination delay. Doesn't mean that it doesn't have a propagation delay. But at any given time, at any given set of inputs, you may not see this. But the circuit will react if it's reacting between shortest this time and longest this time. There was one more question, I think. No. Nobody ran out very quickly, raising their hand? No. Okay, now, remember those abstraction levels? So if you were in EE, if you were visiting VLSI 3, we would go on, characterize these propagation delays, contamination delays for a long, long time. But what is usually then given to us is, hey, look at it. These are our propagation delays. When you are solving a problem, when you are a computer solving a problem, these gates are pre-characterized. You know, if you're making chips in, I don't know, 7 nanometer technology, you have actually a library. That library contains all sorts of and or gates and combinations. And literally, there is a textual description that says the propagation delay from input to output for this gate is, in this case, 60 picoseconds. Picoseconds, we were at nanoseconds, 1,000 of it is picoseconds, so 1,000 picoseconds is 1 nanosecond. So these are quite fast, you know, 30, 60, 80, 90, 50, 35. It's from a textbook, right? So we are just using nice rounded numbers when we ask exam questions that things round up, and students don't complain that they need a calculator. Yes?
Is it like an upper bound level? Like after this type of amount, we can be more or less sure that the resulting thing is correct?
That's the definition of the propagation delay, right? Not more or less. There's an agreement that says, wait for propagation delay, that output will be that. You know, sue me, kill me, do anything. Okay, so given a set of circuits, now this is a typical POS circuit, right, product of sums, and you realize that from the input, I still have an inverter. So in the worst case, I'll do one inversion, then I'll go through this 3-input AND gate, and then I'll go out of this 3-input OR gate. And now I can go and look at the system and calculate. There's a propagation delay of inverter. Look up the, oops, where is it? Sorry. Look up the table, 3-input AND, so much. Write down the number, inversion this, sum them up, and hopefully you have a number for these things. Now, given these circuits, it's easy to calculate it, okay? So there is no problems about it. Now, while we're talking about it, there is a similar event. The difference between contamination delay and propagation delay may mean that while the circuit is still figuring it out, remember the bear, while he's still doing the calculation, instead of he saying 4, he says, oh yeah, it's 3, no, 5, no, 4, you know, changes the mind a couple of times. So what happens is the output may, the input change can cause multiple output changes before the propagation delay is finished. So it may change his mind once, then change his mind again, then change it again, then change it again. We will see this later when we are coming to adders. There's a very famous example where the circuit just goes bananas. It's just like, no 1, no 0, no 1, 0 for the longest time. So coming back to the question that was asked, either this is a huge problem for you, where you rely that the circuit output only changes once because you want to operate with it, and you want to prevent it. And if you are in that kind of discipline, the ones that your colleague was asking, this is a huge problem. You have to fight it. We will see later on how we address this. We don't care. The circuit can go bananas, It can go 1, 0, 1, 0, 1, 1, 1, 0, 0, whatever, dance around, change his mind. He can do whatever he wants. The basic thing is, when the propagation delay is finished, I want an answer. Before that, hey, whatever. I mean, everything is welcome, Be the best circuit you can be. I don't care. Now, why are we talking about this then? You will, later in your course, also have simulations. You will see how a larger logic circuit is working. And it's important to realize that the output of a circuit, combinational circuit, can change its minds a few times. And we call these glitches. And glitches can happen because of a number of things. Now, there is an example, and I'm not going to go too much into detail because they also want to prevent it. This thing we will not cover in the exam, okay? Knowing what a glitch is, yes. Trying to prevent glitches, I say no to that, okay? But here is what is happening. So they have a condition. The input was A was 0, B was 1, C was 1, and then this is the critical path going out there. And if you follow this, and if you give the delays to those gates, you will see that the moment B changes, N2 will change, and then N1 will change again after a little while because there's an inversion there. And so in the meantime, Y will for a short time drop to 0. And then after N1 changes, we'll come to his senses and then revert back. So the output technically will not be changing. It will still stay at 1. But while these signals are propagating through these gates, at some point, for a little while, he will think, the output is 0. Oh, no, it's 1. Okay? And it's just for you to realize, I mean, who's here concerned about power, energy, the amount of energy we waste? So many people. Okay. I'll turn off the lights. Okay. You have to realize that this is not really helping to the computation. Every time a circuit changes its mind, we are wasting a little bit of energy. So glitches will waste energy, for example. That's sometimes why we care about them. Functionality-wise, we have given up on this thing, and we say we know that it will go back and forth. I don't care. I will manage this in a different way. So I'm not talking about fixing glitches, not part of the exam. Why understand glitches? Well, they don't cause problems because we have a way of dealing with them, which is coming next week. The week after. But when you are looking at simulations and other things, it's good to realize what they are. It's good to know what's happening. So you can say, well, this is normal. Circuits can glitch. And this is what we call a glitch. It's not only in the matrix. Who's watched Matrix? Okay, at least. Okay, so this concludes actually the part that we want to talk about, the combinational circuits. I still have 15 minutes. What I want to do is I want to give you a glimpse into Verilog. So allow me to just try to switch the presentation. Oh, it's there. So great. Okay. What? No? I got scared. Somebody was rushing the stage. Okay, so let's get started. We will not finish these slides. We will continue next week, but let's just give you an introduction to Verilog. And what we will do is, now we are covered the combinational logic. We will give a brief introduction into Verilog, explain why this is the greatest thing ever. And then we will learn how to describe combinational logic circuits in Verilog. After we've done that, we will then go back to our circuits again and cover the sequential circuits. Then we will learn how to describe sequential circuits in digital circuits, and that will allow us to design any kind of thing. Now, part of this thing is going to frustrate you a lot. Okay, I understand. So the problem is you are too young. There's nothing wrong with that. You didn't live through the changes that happened and that brought us to the mess we are in. And this happens a lot. The first thing that you will do after I go through a few slides of the Verilog saying that this is such a stupid way of describing hardware, let me design my own language. A lot of people do that. Please don't. The language is stupid, but it works. So in the beginning, why did it come up? Why is it the way it is? I can tell you the stories because I like stories. So in the beginning, people in different parts of the world were drawing their circuits. So they had these circuits drawing techniques. So they said, okay, this thing should come like this, it would come like that, go here, there's a multiplexer, 0, 1. And so they were drawing it. And how do you transmit this thing that you've drawn in Zurich to Geneva? Well, you print it on a paper, you give it to a horse carrier, whatever, he rides his horse, goes other way, they open this thing, put on a table, try to understand what you did it. Horses were probably not involved, but people used to send these drawings printed on large-scale papers, A3s, whatever. Then they scanned them, faxed them over, fax machine. Yeah, okay, good. And it was difficult. It was difficult for people to communicate and draw these, exchange these drawn things. So they said, isn't there a way how I can make these schematics? Let me just show you. Instead of, and this is true, right? So this is from 1986. That was when it was issued. First revision, 15th of December, 86. And the last revision, 26th of January, 1987. And there is all kinds of things. You see them very little. There are these ICs. There's a couple of capacitors. Here, there's a NAND gate. Here's an inverter. Here's an AND gate. Oh, my God. And they sent this. And you sit down and you argue about it. And you say, hey, Marcel, that AND gate over there, I don't like it. Can we change it to an OR gate? And says, which one? And it says, yeah, roughly 2/3 this way in the middle. The one that says A300. It was difficult. So the way the HDL language, they said that we need a hardware description language, was literally to translate this in a text form. That was their only reason. That's how it started. Verilog started as a textual way to describe schematics of interconnected circuit elements. That's what it is good at. And then you realize that these are boxes, and inside these boxes, maybe there is more of them, right? For this, there's another sheet like that, and maybe there is something. And then somewhere you come to like this basic functionality that everybody understands. There's an AND gate, an inverter, something, something. So you understand what's going on. Now, what they wanted to do is they wanted to model the interface of the circuits, meaning that what's the input, what's the output, how they were connected between them, and supported some of those nice and well-known logic functions like AND, OR, NOT, XOR, and maybe multiplexers because Frank likes them. It was a very convenient way. It was standard. It wasn't proprietary. It wasn't belonging to one company or the other one. And the great thing was, it was machine readable. So you could use computers to read it, to translate it, send over emails, do other things. Now, the additional benefits were discovered later. So we were using HDLs much before we could synthesize them into actual working circuits. We could, using HDLs before we could use simulations to show us, hey, how does this circuit work before I even construct it? So, like many, many things in this world, when people come up with one thing, they can never agree on something. So immediately, they, at the same time, look at it, this is 1981 and then finished in 87. That one started in 1984. More or less simultaneously, some set of people came up with Verilog, and a different set of people came up, no, ours is much better, VHDL. Both are horrible. And both disagree on like almost anything possible. For example, VHDL is case insensitive. Of course, Verilog has to be case sensitive, right? I mean, the case sensitive people, the little endians, no, case sensitive is the way. So we ended up with these two different ones. In this course, we will use Verilog. We had to use one. Traditionally, we ended up using Verilog. Didactically speaking, it's the harder one to teach. So my job is harder. And you have an excuse to say, Frank didn't teach it well. Now, let's just get a little bit started. Remember that the Verilog is all about describing this interconnection. It will look like a programming language. It will look like C. However, it's not a programming language, not at all. Every time you see a Verilog code, please, in your mind, imagine this, okay? Verilog code is this, nothing else. Now, what we want to do is, well, we want to give and say, describe a circuit. We will call it a module. That's the Verilog nomenclature for it. We have a set of inputs and some outputs. So this is what we want to describe. And it looks like this. Very simple. You say module, give it a name, in this case, example, not very creative. And we say, there's a bunch of connections. We call them A, B, C, Y. And A is an input, B is an input, C is an input, Y is an output. And now somewhere, we didn't describe it yet, we will describe what happens inside. And then, and module. This is it. This is the basis of every Verilog description. You take one file, you say, I'm going to describe a circuit, that's the name, those are the inputs, that's the output, and somewhere inside, I'm going to have the things. Now, over years, people started agreeing and disagreeing over a lot of things. So, for example, this is one way of writing. You say, hey, this is my module called test. It has the A, B, Y, and A is an input, B is an input, Y is an output. And people said, that's stupid. Why don't we say module test and describe the input A, input B, output Y in the header? They're both the same, okay? You can use them interchangeably. Over time, what happened actually was that a lot of the stupidities of Verilog were ironed out, and there are many. And when they ironed out these stupidities, they said, we are going to change the name of the language. We are going to call it System Verilog, like a better Verilog, which would have been a great idea, but they made a cardinal mistake that everybody makes and said, oh, by the way, System Verilog is backwards compatible to Verilog. So any stupidity that you can do in Verilog, you can continue doing in System Verilog and still call it System Verilog. Now, remember that I said that the book has the older edition and the newer edition. The older edition only has Verilog. The newer edition has System Verilog. And they are, you know, codes can be on both sides. It's just that the cool parts of System Verilog are so much more difficult to explain if you don't know what the stupid way of doing it was. Because it solves some problems, and if you don't know what the problems were, you will never appreciate why they are doing it. You will say like, that's a very weird way of doing things. And say, I agree, it's a weird way of doing things, but you didn't know Verilog. So this is why I'll be talking more about Verilog. It's also easier to approach and to talk about. Okay. So these were single bit signals. A was 1 bit, B was 1 bit, Y was 1 bit. Can I do more? Of course we can do. We can then define ranges, and we can say, hey, the range starts from here, colon, range end. So we can say input A is not 1 bit, but is 32 bits, ta-da. Or it's actually 8 bits, but I'm describing the bits from 15 to 8. Or is 8 bits, but I'm describing, I mean, it's an array from 7 to 0. Or it's a single bit. Wow, great, we are doing circuits. So, annoying things. Verilog is case sensitive. So some name and some name with different capitalizations actually refer different things. Don't even do it, right? I mean, just be consistent. Don't mix your styles. It's just asking for trouble. Names cannot start with numbers, so too good is not a valid name. White space is ignored. And you can have single line commands that start with // You can also have multi-line commands. People, please don't use this in Verilog. I mean, you don't want to have commands that go, I mean, commented out parts of code that you scroll over multiple pages and, you know, somewhere there is this and you rely on the syntax highlighting to show you. Don't do that, please. So, good practices. Develop and use a consistent naming style. Because it's case sensitive, trying to use whatever it is, you know, if you want to use camel case, use camel case. If you want to use all caps, use all caps. Just don't mix it, okay? Have a style, your own style. I mean, if you're working in a company, they will most probably enforce a style. If you make your own company, develop something. Use most significant to least significant ordering for buses. So try using 31 to 0 instead of 0 to 31. You computer science people, okay? Most significant bit to the left. Why? Because if you say 31 to 0 and you write a number, 1, 1, this is bit number 31, this is bit number 30, this is 29, 28, and this is bit number 1, this is bit number 0. So writing a number from 31 to 0 makes more sense for people who are seeing ones and zeros like written out like that. Okay? People like it that way. Okay. Oh. Now, the module, nobody puts you any limits. You can make your migrators, you can say Apple M2 dot file and start writing module after module. Not very smart. Define one module per file. This is just a style question. It's much easier. Second, use a file name that equals module name. So if you have a module try this, try to put it in a file called trythis.v for Verilog. Now, if you want to rebel, color your hair, have a tattoo, some piercings, move to Africa, I don't know what. Do something, just don't rebel here. Okay, don't say trythis.v contains the module, not doing that, or something like that. You know, it's not worth it. We will spend a lot of time trying to find mistakes in our circuits. So we don't want to make our life unnecessarily difficult. Okay. So this should give you a little bit of taste what's coming on next week. So next week we will talk more about Verilog and then continue into sequential circuits. I wish all of you a great weekend and hope to see you next week.